Hello everybody and welcome to Mathematics with Comvest. Today I'm going to be starting something a bit different, which is the field which I've decided to dedicate my life to studying, and that is mathematics. In this particular case, it's going to be something foundational, axiomatic set theory, and I'm going to be using Patrick Suppes' axiomatic set theory in order to, attempt to articulate properly some of the valuable lessons to learn from this work. So without further ado, let's get into it. So starting with section 1.1, we have, whoops, I already forgot to write that down. Oh well. Set theory and foundations of mathematics. So what exactly is a number? That's an interesting question, right? You know, you could sort of define it as abstract representation of physical elements, something like that. I mean, there's plenty of things that you could do that would also fulfill that definition, though. Well, way back in ancient times, there's this fellow by the name of Eudoxus, who comes up with a theory of proportion towards answering that question. And you can actually see that, and this might be something which, if we're lucky, could be on Classics with Comvest, is in Book 5 of Euclid's Elements. And in it, he tries to give a rigorous treatment of irrational quantities like the geometric mean of 1 and 2. Which is a pretty big deal if you know things about early Greek mathematics. They were really concerned with rational quantities. They didn't really, a lot of times they didn't really mess around with rational quantities. So Eudoxus really tries to get at a theory of proportion towards that question by answering it using this. And so we get sort of like an ancient foundation of a foundation towards set theory. So let's get a bit closer here to today's time. And that is by mentioning George Cantor, who around 1870 came up with the theory of infinite series. proof that the real numbers, which I'll denote as just this weird looking R here, you'll see, that the real numbers don't have a one-to-one correspondence with the natural numbers, which I'll denote with this N. She proved in 1874, and in 1878, he proved that two sets being equipolant, so that just means equal in power, so yeah, or having I wrote that down, having the same power if they can be put into one-to-one correspondence. And George Cantor came to be known as the father of modern-day set theory, and his works go far beyond this, as we'll see later on in this lecture. But for now, just going to the foundations, we see here the early groundworks for set theory, with the theory of infinite series and proof that the real numbers don't have a one-to-one correspondence that some of you may have seen in real analysis, two sets being equipotent or having the same power if they can be put into one-to-one correspondence with each other. So all of these ideas and the idea of proportionality that we got to Eudoxus are all coming together to get to our modern understanding of set theory, which George Cantor deals with is called naive set theory. It isn't really broken down axiomatically speaking. So let's get into some of the axioms. Assuming you all know the notation for the set theoretical notation. Set theoretical notation. It's kind of a weird way of putting it, but it's apt. So I'm just going to skip section 1.2 because that's basically just a whole bunch of notational stuff that I'm assuming you'll all know, or I'm assuming that I can properly mention within due time. Like, I don't see the point of like dedicating an entire section to it, unless if you're like, really a beginner to it. But if you look across a video that says axiomatic set theory as an absolute beginner, I assume you have your wits about you and already are able to pick up on set theoretical notation on the fly. So there's also that. So section 1.3, axiom schema of abstraction and Russell's paradox. So Cantor's proofs, like the ones we saw earlier, they operated off of three axioms. First, these. The axiom of extensionality. Of sets. Oops. And the axiom of existentiality of sets asserts that two sets are identical if they have the same members. So that's reasonable enough. You know, we like our axioms to be that way. We like our axioms to be, well, I guess that reasonable enough is sort of a bad way of putting it, because we like our axioms to not rely on any underlying assumptions, because the axioms themselves should be the underlying assumptions. Then we have the axiom of abstraction. So this one states that given any property, now let's throw in some notation here. This little backwards uppercase E, I guess you could call it, stands for there exists. So states that given any property, there exists a set whose members are just those entities having that property. And the third axiom, so yeah, just to reiterate, the axiom of abstraction states that given any property, there exists a set whose members are just those entities having that property. So if you have so given any property, like out of all the vegetables, you have a set of canned vegetables. There exists a set whose members are just those entities having that property. So all of it's the set of all canned vegetables and the set of all preservatives. So this third axiom, the axiom of choice, is really important, and so you always have to save the best for last, and so we're going to save that one for later. And instead, we're going to turn our focus to the problem of the axiom of abstraction and how we exactly get a paradox out of that. So, the axiom of abstraction. Its first explicit formulation was found as Axiom 5 in a work by Frege in 1893. It isn't until 1901, well, I guess 1901 was pretty close, that Bertrand Russell, mathematician and philosopher, finds a contradiction. Now, what is this contradiction? The set of all things which have the property of not being members of themselves. And this is what comes to be known as Russell's paradox. So you're trying to get a set of all sets, and you just can't do it because the set of all things which have the property of not being members of themselves. You'd have a set which is of itself and not of itself. And so that's a contradiction. But let's look into the formulation of the axiom of abstraction and see exactly how it breaks down logically within the proper notation, which I will be sure and talk about accessibly. Yeah. Okay. So we have that there exists y such that every, this thing says, this thing means for every x contained in y, x is contained in y, this thing means if and only if x is contained in y, if and only if the function phi of x follows. So that's sort of the, it's kind of getting at the property. Where phi of x is a formula, yeah. Where y is not free. It's not a free variable. Oops. Now we want to show that this formula asserts that x is not a member of itself. So, tangled in the microphone wire there. Oh yeah, and by the way, this statement if and only if, this here means if x is contained in y, then we have this formula. Conversely, if we have this function, then x is contained in y. So it goes both ways. That's why you have the both ways arrow. This one does not have the both ways, so this means just like this symbol right here is not, so not x in x. If not x in x, then. So this goes if, then. If then. Conditional. It's called a conditional. Then we have that there exists a y for every x, such that x in y, x is in y, if and only if, if and only if we have not x as a function of x, not x. So then we have y within y, if and only if not y in y, with x setting x equal to y in 2. Now, y being in y and not y, being in y, that's a contradiction. So contradictions are usually denoted by this, and end of proof sign right there. So there we have a bit more formally how exactly Russell's paradox arises as a contradiction. So let's try and look at the axiom of abstraction in a particular way to see how we can maybe formulate a different means of preserving its essential properties and disregarding that property which makes it lead into a contradiction. So if we think about the axiom of abstraction a bit more abstractly here, is that the axiom of abstraction is really, well, it's not finite. It's really an infinite bundle of axioms. When we just start replacing the formula, the expression, phi of x in 1 by any formula. In which y is not a free variable. We have a new axiom for each of those scenarios. So what is this sort of axiom called? There's actually a term for it. This little axiom of axioms. So axioms that permit blanket substitution of formulas are known as axiom schemas, like a schematic for like a house or something. So this is quite reasonable because you have, a scheme is just, it's a scheme for making assertions. Schemy. And for making is just one word, and that wasn't an accident at all. It's just one word. You may not have known that. So is mathy. So the axiom of abstraction is really this infinite bundle of axioms when we replace the expression by any formula in which y is not a free variable. That's supposed to be we have a new axiom. Axioms that permit this sort of thing are known as axiom schemas. The axiom of abstraction is an axiom schema. So, well, how do we deal with the problem? Right? How do we deal with the problem of Russell's paradox that we have a set, we can't have a set containing all sets? How can we sort of rejigger this into getting a better axiom? So, Ernst Zermelo in 1908, he came up with the axiom schema of separation. Sonderung axiom. Yeah, probably butchered that. Oh well, I'm American. So, what he basically states is, if we know this is an instance here, if we know the set of animals exists, we may use the axiom of separation. To assert existence which assert the existence of the set of animals which have the property of being men. I.e., that is, the property of being human. Enables us to separate men from animals. Yes. So, Ernst Mello, 1908, axiom schema of separation. If we know that the set of animals exist, we may use the axiom of separation to assert the existence of the set of animals which have the property of being men. That is, the property of being human enables us to separate men from animals. Now, let's look at this a bit more formally, a bit more generalized. So, there exists a y for every x such that for every x and y, no, sorry, such that if x is in y, then x is in z, and our formula from earlier. And if x is in z, and if we have our formula, then we get that x is in y. So, one asserted from earlier, one, the axiom of abstraction, asserted the existence of sets unconditionally. Whereas this one here, let's label it star. Completely conditional. So notice that's really important. So one asserted the existence of sets unconditionally, whereas this here, this formal axiom schema of separation, makes it completely conditional on whether or not we know that the set already exists. So we have to be given we have to be given the set Z. Then we can assert the existence of the subset Y. So does the set of all sets exist? Well, no. Well, then we can't use that. So there we go. It's kind of a way to sort of tiptoe around it, you know. Well, no, it's very loud. It's very, very loud. It's not a tiptoe. So yeah. Alright. Actually, let's label this as 5, since I'm going to be working on this one. So let's try and break this thing, like how we did with the axiom of abstraction. We broke it. We proved that there was a contradiction. We couldn't use it, and so we got rid of it, replaced it with the axiom of separation. Well, let's see if we'll have to separate from the axiom of separation here. So, here we go again. Not x and x. There exists y for all x, in which x is in y, if and only if x is in z, and we have this negative looking bud here. And we get x equals y. If x equals y, then y is in y. Y is in z. And negative, not negative. Yeah. And we have that we don't have that y is in y. Concretely, let Z be a set A, which is equal to the singleton sets 1 and 2. So we have that there exists y such that if y is in y, if y is in y, if and only if a and, this is an ampersand by the way, that means and y is not, and not y and y. There we go. So choosing A itself, as an appropriate y for for A lens it is not a member of itself. So the left and right sides would be false. Since it's an A and not A is contradicting. So it takes care of that contradiction that we had earlier. It's like, nope, that's false, can't use it, move on. So there we go. There we have the axiom schema of separation and how it deals with Russell's paradox. Yes, by of course making it conditional, that we know that the set already exists. So this stems from the fact that Zermelo, in 1908, formulated this axiom schema. He formulated the axiom schema of separation in terms of questions or statements which have the property of being definite. What do we mean by definite? Finite, right? So, a statement is definite if it can be decided. In an unarbitrary manner, in a non-arbitrary manner, whether or not any object satisfies that condition. So, going back to that conditional argument over there, making it conditional that we know that the set exists makes all the difference to this exchange of axioms. So let's write down the axiom then. Oh yeah. Just to sort of reiterate, the axiom of separation He formulated it in terms of questions or statements that have the property of being definite. A statement is definite if it can be decided in a non-arbitrary manner, whether or not any object satisfies the statement. Paradox is being erased there. It's kind of symbolic. Okay. So, the axiom of separation, stated in just regular English, as far as mathematics gets to regular English, is as follows. If a statement, like our formula from earlier, phi of x, is definite for all elements of a set M, then, whoops, there is always a subset phi of M which contains exactly those elements x of M for which phi of x is true. So there we have it. The axiom of separation. If a statement phi of x is definite for all elements of a set M, then there is always a subset M sub phi of M which contains exactly those elements x of M for which our formula is true. And there we can erase Russell's paradox. Okay. Now the first classification of this notion of definiteness, it actually doesn't come by somebody that would be appropriately more well known later on. So Skolem gave the first classification of this notion of definiteness. He characterized it a definite statement as just a statement which would satisfy his exact formula. His exact definition of formula. Yeah, so you have a formula that's defined a certain way, the set has a certain property, definite, definitely. Yeah, so Scullin gave the first real classification of this notion of definiteness. Characterized a definite statement as just a statement which would satisfy his definition of formula. So the way that you define a formula, that's definite. It's simple enough, but very influential idea. And I mean, everything that you see now looks really simple. You know, hindsight being 2020, but this year being 2023. Frankel, in 1922, actually modified this to the axiom schema of replacement. So it doesn't really require as much restriction to definite statements. We'll get into that later. So what we're running into here is Zermelo-Frankel set theory. But with Scullin involved, it would be more appropriately called Zermelo-Frankel Scullin. Not Golem, Scullin. Though that does sound quite heinous, sculling somebody. I don't even know what that means. Yeah. This guy is usually not included, so wah, wah. Zermelo-Frankel set theory. But Russell's paradox isn't the first or the last of paradoxes that would come to shape our mathematical world.